My name is Andrew Coble, and this is my Project 9 presentation for CE 570. Alright, for this project, I wanted to start out by outlining some of the objectives. So assume the composite body is the deformed body. Define a symmetric Cauchy stress tensor field S of x. Compute body force density needed for equilibrium, which is just equal to the negative divergence of S. And then verify the total force on one of the body parts. And then right below is my symmetric Cauchy stress tensor field from last week. This slide is a repeat from last week. It's just a quick overview of what my stress field looks like when you apply it to each of my bodies. So here's my stress field up on top, and then that it's applied to the hemisphere, and then the cylinder, and then the upright cone. And you can also see my MATLAB code of each of the stress fields respectively. Alright, so the main objective for this week is that we need to calculate the body force density acting on my body. So as you can see, it's just the divergence. I'm calculating the divergence of S here, which is just the vector 1, 2, 8. And then the body force density is just the negative divergence of S, which is negative 1, 2, 8. And then you can see I apply that to my hemisphere, which is just negative 1, 2, 8, since there's no variables within that vector. And the same applies for the cylinder and the upright cone. And then these are also the snippets of my MATLAB code with my hemisphere, cylinder, and cone respectively. This slide just outlines that I chose the part 2 body, which is the cylinder, to verify the total force. And then on the right hand side, you can see my stress field generated from this week. As I said previously, the total force that I decided to verify was on my body 2, which is my cylinder. So you can see the vector, the body force density vector defined on the left-hand side. And then on the right-hand side are my total force calculations. I started by triple integrating over the body force in dV. So that is the limits theta, r, and z. Theta is from 0 to 2 pi, r is from 0 to 4r, which is just 8, and then dz is just from 9h to 10h, which is just 18 to 20. And then dv is technically just, and then the volume Jacobian is just r in this case for the cylinder. And you can see me calculate each of that out, and the final answer is negative 402.1239 E1, negative 804.2477 E2, and negative 3216.9909 E3, and that is verified below for my MATLAB code. Alright, so I'm just going to do a quick overview of my code. So first off, here is the first part of my body, which is my first body, which is the hemisphere with radius 4r. We have all the same variables from these past couple of weeks. The only portion that we added was the body force density, which is negative 1, negative 2, and negative 8. And then here's also that Cauchy stress field from last week. Second body is the cylinder with radius 4r and height h. And here is the stress field, and then the body force density right here. And then for the cone, we have the Cauchy stress field and then the body force density right here. And then here is the same stress field from prior weeks. We'll run the code real quick. Alright, so here you can see my stress field defined. And then here are the command window outputs for the surface areas, and then also the volume and the total body force and the total force on the surface and the bodies respectively, and then the net force on the total composite body.